My name is Johann Fischer. I'm R&D engineer for Nordic Semiconductor, and I'm also a USB subsystem maintainer for Zephyr project. Welcome to my talk about USB support in Zephyr project. I will give a quick overview about our state and planned work for this year. I will not get in detail about USB, about new USB device APIs in detail, but give you a quick overview. So what's about today? Yeah, it's about USB support. It's a continuation on the presentation from the last Zephyr Developer Summit. It's not about current USB device support in Zephyr, yeah, which is not that bad, but has few limitations and drawbacks and issues. So we decided about a year ago to start with a rework of device USB support and driver API. So what's going on in USB development in Zephyr? We will have new USB device controller driver API. We will have new device USB stack, and the current device support will stay maintained until we moved everything to the new one. That means we have to port all the drivers to the new UDC API and all the classes we support to the new device stack. What's hot and new is this year is initial USB host support, which contains USB host controller driver API and yeah, initial host stack validation, which is very simple. Yeah. Yeah, USB device controller API. We will actually, the new implementation fixes few limitations for that we have in current one, like support for multiple drivers and instances of the driver. So with the current, it's not that necessarily. I mean, that will not be used that much, yeah, because usually have just one device controller on new SoC, yeah, or on a new board. But we have in Zephyr we have boards that has many USB device controllers, like IMX IT 1050, yeah, and the new the new device API. We have support to query controller capabilities, like if it's a host full speed controller or high speed controller, does it support remote wake up or not? We will have better support to check endpoint configuration. So in comparison to the current one, it's not possible if a specific endpoint supports, for example, isochronous transfer or not, or what is the maximum packet size of the buffer of the controller. New API has a single asynchronous API to enqueue transfers. We will not have functions like endpoint read or endpoint write, which is very confusing in the USB context because you cannot write to the host. Yeah, it's USB works different if the host dominates everything. If host doesn't like a transfer, the buffer will stay untransferred all the time. Yeah. The new API uses net buffers for endpoint transfer. That's its topic for a different discussion. Yeah. But we started with that approach, and we use for the meta information about data transfer, we use this area in the net buffs. And there is a thin common layer for all the drivers. So the driver doesn't communicate directly with the upper layer. There's a common layer for all the drivers that implements locking, some helper functions, and handlers or functions to submit an event to upper layer. I have implementation for NAF USB-D controller, which is full speed and can be found on an NAF device like NAF52840 or 5340. And I have a working implementation for Kinetis USBIP OTG controller, which is a different one, and it's NAF implementation uses shim approach, and Kinetis USB OTG uses it's a native driver, and Kinetis controller is a simple one. So it's if someone starts to would like to add another driver, so there are two that can be used as reference. So we have in the driver bar we have actually two APIs for each driver in Zephyr. The one is that driver faces, and the other one that is for upper layer. So here just a quick overview about driver facing API. That's what is already described. Here is the one thing is that unlock and lock functions for mutual exclusion. So the driver, for example, doesn't have to implement it as an own. There is a common implementation for that can be used, but if for some reasons it's not possible that the driver can implement on his own. Yeah. The differences to the current implementation is on the top. For example, there's endpoint NQ and endpoint DQ functions, which will be called for common layer, but every driver has to implement it on its own to put the transfers in the queue. We don't. So you can see there's UDC AP config structure, for example. So the difference is to upper layer facing API that it doesn't. So this config functions is internally for UDC layer. So the upper layer here doesn't use it. It just passed always the endpoint address here, like endpoint to the common layer, and doesn't care about it. So it's it's a kind of simplification for the stack to handle this API. The other difference is that there is an endpoint try configuration function, which is used by upper layer to check on configuration. So it can pass all the attributes for endpoint like isochronous transfer, packet size, and so on, to the common layer of the driver, and it's either successful or return some specific error codes, like if the a parameter of wrong or just not supported. Yeah. So that's just as reference how the structure of the new implementation. We put everything in new namespace called UDC. Because device was already reserved here by the current implementation. So, yeah, that's about UDC API. Any questions related to? No.
Yeah, maybe just quickly. I was looking at the endpoint. I didn't see. So you're enqueuing a request to an endpoint, right? So how this works.
Yeah. So a request is always to an endpoint. Yeah.
And then that gets translated into enqueuing into the USB, the actual hardware peripheral. the driver level. So going back one more, right? You have I think UDC and Q.
Yeah, sorry, you mean here UDC P and Q?
Yeah.
So the endpoint is stored in the metadata of the net buff.
Ah. Yeah,
Okay. So and common layer encodes that, and actually it's just the endpoint configuration is a lookup table. Yeah. And based on endpoint address, it takes the proper configuration and calls the driver with configuration structure. So it's in first iteration I used a linked list. It's also in the current pull request, but I changed it because lookup table is much faster. So with the implementation mechanism, I reworked that a bit, and it works better. So yeah, that's what I forgot to mention. So the driver has to initialize a table with his endpoint configurations, and then common layer transfers that depends on metadata too. Yeah. The same for the synchronous codes like Z address or no, sorry, not that endpoint halt or halt clear. Yeah, so that's puts the endpoint in the state to reply with stall handshake. Yeah. Yeah. In USB device stack implementation, like UDC API, it supports multiple. Like UDC API supports multiple drivers, it supports multiple UDC instances, and has also support for multiple device configuration. In the current support, we have just one configuration. It's hard-coded. Also in device request, it's always response with 1. Or sorry, but with 0. It depends on what you want. If you ask for the script, it's the index, right? Yeah. And here we have support for multiple device configuration. We can update and set attributes of the device, like vendor ID and product ID at runtime. So the current approach, current stack is static, yeah. But the user configured at the build time can be changed. We fix that here. In device we can change device attributes and also configurations attributes, like how much is power consumption. So if it's self-powered or bus-powered device. New implementation has class and function. Also, it's confusing with USB spec uses functions. Internally we use class as name, and that will have support for multiple classes, class instances, and assignment to a configuration at runtime. So if we have multiple configuration, we can assign, for example, first CDCSM class to configuration 0 and second CDCSM class to configuration 1. And or second configuration class can have, for example, another class like audio and so on. So the endpoint assignments from the classes are done by the stack. So it's up to the stack to handle that with lower layer with UDC if that endpoint address can be used with specific attributes or select a new one. Yeah, it's like kind of automatic configuration we have in with the current stack was much flexible, and there will be car config option to disable that. That's yeah, some people ask for that because they would like to use some hard-coded endpoint addresses in few Linux kernel drivers. Yeah. So the interface configuration is done by the stack, and we will have managed endpoint transfer events. So there's a single event message queue from the lower layer, and it's up to stack to like way back machine to find the right class instance for to forward results from the transfer, from the endpoint transfer. Here's a raw overview about all the layers and internal APIs in USB, new USB support. Like I said, we can have multiple configuration, multiple class instances, and we will also have USB event broadcaster. If I, yeah, that's on the next page. I will describe that a bit in detail later. That's an example what will change for the user. Yeah, in the current stack, the user, it's up to user to enable USB or disable that, but there's not much the user can change. Yeah, it's just one: enable or disable, nothing more. And with new device implementation, we will have all the functions to configure the attributes of device and configuration, and initialize and enable the stack. So it's up to user to define configurations. They can use either the macros from the header, or define all the structures on yeah. And the same for the descriptors and devices. It's also up to the user to provide the device instance during initialization. So this USB device defined macro can be used many times with the same device. Yeah, but you can initialize that just once. Yeah, if it's just initialized, this will be blocked. Yeah, but if you shut down the USB, you can use another one, a USB context with, for example, different vendor IDs and product IDs, and reuse it, enable it, and as initialized and enable it. So the important thing is there are two steps. The first one is to initialize USB context, and the second one is to enable one. So after the initialization, the controller is prepared, but is not recognizable by the host. Yeah. The reason is that if I have a device with, for example, USB charger device, yeah, after initialization, the user can receive the events from the driver. For example, if someone attach it to a host, so they will be able to receive an event I'm attached to the host and wait at a specific time to give a charger device to be initialized, or initialize a charger device if there is an interface to it. Yeah. And after this specific time, the user can enable USB, and yeah, the same. We have the same functions in another direction, like to disable USB device and shut it down. So it will be completely disabled, and in the future, a way to change the role. If that controller is OTG compatible, so to change the role from device mode to host mode, for example. Yeah, how does it work in simplified in the background? So I described the device configuration are initialized by USB init. It's also all the configuration from all the classes is stored in class descriptors. I will describe it on the next page, but it's in responsibility of USB, you need to initialize all the classes and configurations and prepare that for the USB enable. So the device stack provides an event callback. that is using by UDC init in the lower layer, and UDC driver submits an event using that callback. Yeah, it's common for all the drivers, and yeah, as I said, devices will not be recognized by the host until UDC enable is called, and yeah. Finally, the host enumerates devices, Z-alto configuration interface alternatives, and the stack also configures endpoint according to class interface descriptors. So for the classes for the user who implements its own class, there's a simplified interface, yeah, in comparison to the current approach. It only contains class interface descriptors and specific API. Yeah. So this class internal API is used only by the stack for the classes. Yeah. It looks like our driver API in Zephyr, but it's much simpler. It has just a few items, and class instances use an iterable section and a specific name to be recognized by the application or by the user or by the stack. And like if the user enables two CDC SAM examples with CDC SAM1, no, CDC SAM0 or CDC SAM1, and this internal API provides callbacks for configuration, updates, control, interface, endpoint events, and all the suspend and resume events. So here's an example how that's from the class code as example. Yeah, it's a simple API that that USB class facing, and every class has to use this USB define class macro. Which is the first argument is the name of the class, and pointer to API and data structures. Class internally uses as another API, and finally what the user does is to register this class unregistered to a specific configuration. Yeah, if you you can see that on the code listing in previous slides, that user has to call USB class register for specific configuration. On if the device configuration changes, instance can be unregistered and removed. Yeah, that's overview about new USB device stack. What is new this year is the USB host support. It's similar in the structure. It's similar to USB device controller, driver API, and USB device stack. It's the controller API is isochronous, and the host support itself is in initial state. Yeah, it's very simple, and it was initially driven by the need to have a counterpart to device, yeah, for testing and driver debugging. So this USB support, or upcoming USB support, should ideally map to device support features. For example, if we move our USB device CDC SAM support to the new stack, which ideally would have a counterpart of that on the host side. For CDC SAM, just allows better testing and coverage. So the controller API is similar to UDC API. It has support for multiple drivers, which is fits better for host side, because it's usually SoC has multiple host controllers. It's also has support to obtain controller compatibilities, and there is single API for bus and transfer events. Yeah, it's isochronous. It's API that uses the message queue. But it uses a container and not just net buffers for transfer as a containers. It's container that can be put in the double linked list in the driver, and the reason is that on the host side it's a bit simpler to handle everything, but for example, the control transfer are from the host side contain setup, data, and status stage as at once. Yeah, it either fails or it's successful. Yeah, so we have all three buffers at once in a container, and also here we have a thin common layer between driver and host stack, and the current implementation is done with or the driver. There is one driver implementation for Max 3421 host controller, which has SPI interface and can be connected to every device that it's one of the shields that uses this device, and it's connected to an FTK but touched. That's actually from the host side, and as I said, the host support is most was driven by the need for beta testing, and about USB device testing. So the best, that what we not have actually for the current support. Yeah, we have few tests, but it's not that necessary. We can remove that actually for the current stack, and there is no benefit from that. But we need to fix that somehow, and the best way is to test on the hardware. Yeah, it's will provide a best coverage and out density, how that behaves. But we can do that always. So the plan is, or the idea to also test using virtual host on device drivers. So in the future we have two approaches, like closed loop, everything not using third parties support like Linux host, but everything in Zephyr using closed loop to test real host on device controller and virtual host on device drivers. We will probably still continue with in the development with testing to test with test USB and Linux host, and another approach is to use host controller testing using USBIP. We have USB. It's called native POSIX driver in the current USB device API, but it's not right name. Yeah, it uses USBIP, and that's another way to test the host part of the USB support, and also use that for development, for class or application developments for USB device stack. So we don't have any emulated controller or virtual controller implemented yet, but it's work in progress. So just a bit about USBIP. USBIP is used by Linux kernel only. There is no, I don't know any working implementation for for macOS or Windows. Yeah, it's used with Linux only. So what it does, it passes USB device from a server to client over TCP IP, and in data if you use that with Linux, it exports a host controller of one machine over TCP or network to another. Yeah, so if you can extend the tutorials to use Raspberry Pi to extend USB cable. Yeah. There are two references to Linux kernel if someone interested in description of how that works. And new implementation based on USB, a new USB host in Zephyr is work in progress. I had an approach in GitHub, but I closed that because I wanted to wait for the host support. And yeah, that USB IP implementation can be used to export a real host controller in Zephyr or virtual host connected to a virtual device controller. That will be look like that. So everything in the purple is implemented in Zephyr. That's Zephyr code, and this network connection is on the build machine over. It's like we used to test network interfaces on native POSIX builds over TAN. Is a TAN or a TUN? I don't remember what one of these interfaces to connect that over a network to a Linux host. And I know that people already use that in the current implementation to develop applications for USB. It's much faster because you don't have to flash it to a to a specific device, and that can be used actually. Once it's done, it can be used with native POSIX and Kimo or whatever. Also the USB IP can be used on boards that doesn't have USB device controller at all. Just last slide about namespaces and USB support that I would like to use. They are already in the pull request, but still I would like some feedback about that. So for USB device, UDC, for host controller HC, and so on. There are some conflicts with USB in general because the current stack uses USB prefixes for everything, but it implements only a device part. It's already moved to on directory, but we still have kind of conflict because USB prefixes should be used only for common part of device framework, for chapter 9 of the USB specification. Oh yeah. Finished.
For the emulated testing, are you looking into doing any compliance testing in that layer?
Not in virtual part, but what we do at Nordic, we do CV test regularly, USB CV test on Nordic devices with Zephyr upstream and our downstream repository. We can also implement specific tests using virtual driver, but that would only cover like device framework. If, for example, Z specific configuration in not addressed state.
Okay.
That's purely specification or some undefined things, but something like remote backup. We can only test that on real hardware. If that works, how that's supposed to be.
So you're queuing requests to the endpoints, and then or transfers to the endpoints, and then how do you know when you can reset? Like, can you reuse that net phone at some point, or how do you know when that's done? Like, if you know,
There's a FIFO in endpoint configuration structure. So the request can be queued. It's not always necessary. Usually not, but sometimes if you stream something and it's not about real time, for example, like bulk transfers, you just want some, you have something you want to put it in the queue. So there's a queue in configuration that can be used for that. And after the transfer, it's up to driver to remove that from the queue and there's a common function from common part that's where it's callback to upper layer to put that in message queue. So we have one message queue for this notification about finished transfers, which returns the net buffer back here. So the net buffer is up to a framework and to class to free the buffer or use it. It's not necessary to. That's a single queue, but usually if the device enumerates, there will be only the transfer events. So that's not that. For example, it doesn't. So the device will not suspend every millisecond and resume again. So it's once specific event, and that's it.
We probably need